In this lecture, I'm gonna be talking about this paper, Model-Aware Contrastive Learning Towards Escaping the Dilemmas. This paper in 2023. Contrastive learning continuously achieves significant breakthroughs across multiple domains. However, the most common info and CE-based methods suffer from some dilemmas such as uniformity, tolerance dilemma, and gradient reduction, which I've discussed in previous lecture, both of which are related to this term. And it has been identified that uniformity tolerance dilemma can lead to unexpected performance degradation. We argue that the fixity of temperature is to blame for UTD. And so in the previous lecture, we were talking about varying this type of parameter temperature and see the effect of that on uniformity. So we enriched the CL loss family by representing a model-aware contrastive learning, whose temperature is adaptive to the magnitude of alignment that reflects the basic confidence of the instance discrimination task, then enables the CL loss adjust the penalty strength for hard negatives adaptively. Regarding another dilemma, the gradient reduction issue, we derive the limits of an involved gradient scaling factor, which allows us to explain from a unified perspective why some recent approaches are effective with fewer negative samples and summarily present a gradient reweighting to escape this dilemma. So here we quickly review info and CE, which was in this paper that I explained in a different playlist, representation learning with contrastive predictive coding. So NCE stands for noise contrastive estimation, is a type of contrastive loss function used for self-supervised learning. So given a set of n random samples containing one positive sample from this probability and n-1 negative samples from the proposal distribution. So optimizing this loss will result in fxt plus k and ct, estimating the density ratio. This is an illustration of model-aware temperature strategy. Points in red, green, yellow, and blue on the hypersphere denote anchor real positive example and real negative samples, and false negatives. So, since alignment magnitude can indicate discrimination confidence of the CL model, then the alignment adaptive temperature dynamically controls penalty strength to negative samples to balance uniformity and tolerance for samples. So let X denote the unlabeled training dataset. Also, given encoders F and G, instance X sub I is mapped to a query feature. So this is your query feature, Fi. And you have a key feature, so G here is just a key feature on the hypersphere with augmentations. So G may be a weight shared network of F or a momentum updated encoder. Assume that the generated query set and key set are denoted by F. And N is a batch size and K denotes the negative size. Then the info and CE loss of the instance X sub I can be formulated like this, where F sub I, G sub I is the positive pair of the instance, and G sub I denotes a negative sample from a distinct instance. Temperature parameter is tau. Negative pairs can also be incremental form, the same side encoded like ntxn, and the final total loss of an iteration is the mean value of the mini batch. So it's just for one instance xi, and then we sum over all of these instances because we have many instances. Previous work identifies the important hardness-aware property via gradient analysis. For convenience, let P sub ij indicate the similarity between x sub I and x sub j after scale by temperature tau and softmax operation. The gradient with respect to the anchor f sub I can be formulated as follows. So you take the gradient with respect to f sub I, which is your anchor, and here this w is the sum of Pij. It can be seen as a gradient scaling factor, and there exists Pij that, so it is worth noting that sum of that is equal to 1, and Pij hat indicates a hardness-aware property. Uniformity tolerance dilemma. The weight on the negative sample x sub j is like this. This is the weight on the negative sample, which is controlled by the temperature parameter. As tau decreases, the shape Pij becomes sharper and sharper. Thus, a small temperature causes large penalties on the high similarity region, which encourages the separation of embeddings, but has less tolerance for Fn. And a larger temperature makes the shape flatter and tends to give all negative samples equal magnitude of penalties. So there should be a trade-off between them. The existence of uniformity tolerance dilemma leads to suboptimal embedding space and performance degradation of downstream tasks. Selecting an ideal temperature may be helpful, but it is not easy to get that balance. Instead, considering that the fixity of the temperature prevents inferency from focusing both on uniformity and potentially semantic relationships, we design an adaptive strategy for contrastive learning to mitigate this challenge. And the uniformity tolerance dilemma is rooted in the unsupervised instance discrimination. Intuitively, the discrimination of a model will be gradually improved along with the training process. Then the high similarity region is more likely to contain this Fn. A dynamic temperature that changes according to iterations might deal with UTD better. UTD, I mean uniformity tolerance dilemma. However, since the training iteration does not reflect the level of semantic confidence for a CL model, such temperature strategies are still rough and heuristic by now. The more reasonable temperature adjustment strategy is needed to be investigated. What motivates us is the alignment property of the embedding space. Alignment property is one of the most critical prior assumptions for instance discrimination. It means that the representation from a positive pair should have a high similarity. Since there are no label available, it is impossible for SSL to explicitly construct semantic guidance. Instead, different views of the same instance are exploited for self-supervised learning. Alignment represents the awareness of viewing invariance of a CL model, which is the base for exploring semantically consistent examples. So Wang and Isola they formulate the alignment laws as the expected distance of positive pairs. Another significant thing is that estimating the magnitude of alignment is not computationally expensive operation. So the calculation of sample similarities is a required step for CL laws, in which the part of positive pair can be directly exploited for alignment. In this paper, we define alignment magnitude A, this is alignment magnitude, as the expected similarity of positive pairs. Hence, no additional structures and computations are needed. Then the proposed alignment adaptive temperature strategies is like this. So it's adaptive. So if alpha is equal to 0, the temperature degenerates to ordinary fixed case. And this strategy is fine-grained adjusting approach. As CL models are trained by sampling mini batches, A that we define, A can be estimated within a batch to promptly adjust the temperature. As you see, you're leveraging A for our temperature, so it's very heuristic. Gradient reduction dilemma. Some recent work tries to address this problem. The problem is that CL models are typically trained with large number of negative samples to achieve better performance, which is computationally demanding, especially for large batch sizes. So we proved they fall into a similar solution targeting the gradient reduction dilemma, but also summarily propose a simple reweighting method. You see the effect of the temperature and K and the gradient scaling factor. Gradient reduction caused by the sum item. The gradient scaling factor is a sum item of Pij and can be described here. This item has small values for those easy positive pairs, which will reduce the gradient in equation 2 and has been mentioned in year 2022. Therefore, the gradient reduction problem will hinder the model learning, especially for those deeper units in low precision floating point training with chain rule. In addition, a smaller K leads to a significant gradient reduction, as there is an insufficient accumulation of negative similarities. So they have a proposition that says it's a bound of gradient scaling factor with respect to K. Given the anchor feature F sub I and temperature tau, so if your K goes to infinity, then Wi approaches 1, which is its upper bound. There is a proposition, another proposition, that if tau goes to infinity, if tau, the temperature, goes to infinity, then Wi is bounded by K over 1 plus K. And so this is a pseudocode for this algorithm, and the above analysis especially explains why some previous work is experimentally effective. We design an approach for the gradient reduction issue and learning with small negative sizes, which is formal. So we are learning with very small negative sizes. As you see, inside Vi, we have stop gradient. This is the key, which is commonly used. But if you just use detach, then you're doing that, because it's the back propagation would not propagate backwardly, so it is detached. And so the conclusion, they analyze inference and provide strategies to escape the underlying dilemmas. To alleviate the uniformity tolerance dilemma, an alignment adaptive temperature is designed. Besides, we offer some insights in the importance of the negative sample size and the temperature by analyzing gradient reduction. A new contrastive loss is exploited based on these strategies.